quantum computing, and then he has been in ETH Zurich, Texas A&M, Microsoft, and has been for a while at Amazon Web Services, AWS in Pasadena, in the new campus in Caltech. And it's a great pleasure to have him here. And then he's going to talk today about, he will introduce the title in a moment, Moving Quantum POCs Towards Production Readiness. Okay, great. Thanks. Please go ahead. So you have 30 minutes plus 5 plus question, but if you want to take it to 30 minutes, 31, 32 should be okay. No problem.
Sounds good. Thank you, Franco. Yeah, it is a pleasure to be here. Good afternoon, good night, good morning, wherever you are. Franco, one small thing though, I still live in the Seattle area. I didn't move down to Caltech. I decided that it's nicer up here. So thank God for, yeah. Remote work makes it possible.
Okay, good.
Good. So yeah, today I'd like to tell you how we move proof of concepts that we do for quantum devices actually into a state where they can be production ready actually today. Needless to say, not with quantum devices. Now, what I'd like to first start with, and I'm sure that my colleagues Fernando, Oscar, Simone will tell you more about this, is how we structure quantum computing at Amazon and where my team fits in. On the left-hand side, you have Amazon Braket. This is our quantum service where you have different quantum devices in the cloud from different vendors, for example, Rigetti, IonQ, D-Wave, etc. And this is what allows you to experiment with these available devices, especially in a educational setting. And you can actually request credits and experiment with some of these devices in case you want to some research. On the right-hand side, we have our technology brand. It's the AWS Center for Quantum Technologies. We recently went from computing to technologies because not only are we developing our own hardware and software, in other words, also thinking about error correction algorithms, et cetera, but we recently added a Center for Quantum Networking into the mix. So we're already working with quantum key distribution devices to secure the communications from our customers into the cloud. And in the center, I have the Amazon Quantum Solutions Lab I lead. This is a team of interdisciplinary scientists that focuses almost exclusively in helping our customers solve really hard problems, but also figure out how you could solve this on a quantum device in the future. Now, let me give you a very, very, very brief technology review of quantum devices. It'll help a little bit later when I'm showing you some results. You have, broadly speaking, two main classes of computing devices. You have the gate model quantum devices. These are so-called noisy intermediate scale, or NISQ. And they're digital and programmable. And as of today, you have, give or take, about 120 or so qubits. There's different types of technologies. Unlike classical computers that run on silicon, you have superconducting devices like the ones by IBM, Google, Rigetti, and also this is also a technology we're building our qubits on. Trapped ions, IonQ and Honeywell. These are currently likely the highest fidelity devices that are out there. Photonic devices, Xanadu, PsiQuantum. Microsoft is betting on topological qubits. And finally, there's technologies like nitrogen vacancies, silicon qubits, et cetera, et cetera. So these devices are actually programmable, and you can basically encode a quantum algorithm and run it on them. Now, another device class are the analog quantum devices. And here in particular, D-Wave is likely the one that most people have heard of and was the first actual quantum device in industry that you could access. What are the main features of these machines? They're special purpose devices. They're not programmable in the sense of a typical computer. They use quantum effects for optimization. The method's called quantum annealing. You add strong quantum fluctuations and reduce those. Similar to simulated annealing that does it with temperature, try to find low energy solutions. The machine has currently about 5,000 qubits. And as of today, we yet have to find a application, something useful that you see in industry, that this machine can solve faster than classical algorithms. And so you will read a lot of things in the press, oh, this machine does this, it cannot do that, and so on. Reality is that until today, we have yet to find this smoking gun of applications. And they're made out of superconducting devices, like the machine by D-Wave. And soon in Amazon, we'll have a trapped atom device by QA, which works in a very different way, but has some advantages and also some small disadvantages over superconducting systems. Now, let me give you an overview of near-term applications. And the emphasis here is on near-term applications. And give you a little bit of an overview of some of the things that you read in the press and what the reality is. And so if we look at quantum applications, you can broadly speak of two main classes. One is big data problems, something that requires a lot of data. And then you have the big compute problems that might require a lot of data in some cases, but typically are very CPU intensive. And so let me start with big data problems, say database searches. In principle, it's possible. We have an algorithm to tackle this. It's called Grover search that is quality faster than classical counterparts. However, there's some issues that very often are neglected. In this diagram that I show you here, on the vertical scale, you have robustness to noise. And on the horizontal scale, you have or pseudo scale, you have speed up potential. And so you can have no advantage, for example, a classical speed up at 2x. Why is it no advantage? Because you can always take two computers and then you get parity. In the center, you have polynomial speed up. And on the right-hand side, you have exponential speed up. So polynomial, something like x squared, x cubed, and exponential being just some power of the number of, say, variables. And broadly speaking, you can now break these groups into two large classes. On the bottom right, you have what I would call the purebred algorithm. They are like HHL, Shor, semi-definite programming. The nice thing about these algorithms is that they give you an exponential speedup. The not so nice thing is that they're very finicky and not very robust to noise. So it's going to take a long time until we can tap into those. In the top left corner, you have the workhorses, those methods that are very robust to noise, in particular annealers, although let's take it with a grain of salt. Variational quantum eigensolvers, QA, etc., etc. But the drawback is, in the case of the annealer, we only have seen a constant speedup, and the other two, you only really have a polynomial speedup. And polynomial speedups are very problematic because you have an overhead that's often not accounted for in the algorithm. For example, how do you load classical data into memory? And this overhead is large, then whatever polynomial speedup you have at the end is gone. The other issue is quantum device clock speeds can be very slow. And so having a machine that runs at kilohertz paired to a machine that runs at hertz, classical computer, is going to be a very long time until these lines would cross. And now if you look at Grover, it's all by itself sitting down there. Why? Because not only offers a quadratic speedup, but also is not really robust to noise. And so this makes it an algorithm that's very finicky and at the same time doesn't give you much advantages. And so database searches, at least with Grover, are not going to happen anytime soon. The important thing to emphasize, though, is we need many more algorithms with this exponential speedup. So what about big Qt problems? And let's talk briefly about chemistry, material research, pharma, et cetera, et cetera. The figure I'm showing you on the next slide is the appearance frequency of all the drugs approved by the Federal Drug Administration in the United States as a function of their molecular weight in Daltons. And you can see that most of the medications that you can buy have a molecular weight between 0 and about 1,000 Daltons. That's roughly where chemistry lives. Now, of the envelope calculation, you would need about 1,000 logical qubits to be able to study this type of systems. But if you look carefully, if we had a machine with only 100 logical qubits, we will only be able to study this little pink sliver on the left, meaning that the vast majority of medications are currently not accessible. Notice also that I suddenly introduced the word logical qubit. And the reason is that with the currently available noise machines, you need to do error correction schemes that can be a very overhead, meaning that give or take to make one error corrected qubit, the one on the bottom with the hat, you need typically at least 1,000, if not more, physical bits, which means that if you want to do chemistry up to 100 Daltons, you would need about 100,000 or many, many more bits. And so this means we still have a long way to with chemistry, mostly because it's beyond the noisy intermediate scale area. What about crypto? So what if we wanted to crack today's standard encryption schemes like RS-2048? What you see here in this chart are the number of estimated qubits for a NIST system, crack RSA-2048, by different researchers using different implementations of the algorithm, in other words, doing different resource estimates. And you can see that in the last, give or take 10 years, we've gone from over 1 billion qubits down to about 13,000 of them. If you had a fault-tolerant machine, you would need about 4,000 or so logical qubits to be able to crack this. But on the best NIST algorithm we know today, it's 13,000. The problem, however, is that the runtime is 177 days. And so if you think about this, no quantum system that we know today will remain coherent for that long time. So we're pretty safe, especially because we have these post-quantum crypto schemes in place. So I would also say that this is beyond NIST. What about optimization? Optimization is an interesting case, and this is the one that I want to focus into, because the currently available machines, especially the annealers, actually allow you to study what I would call mini example problems of optimization problem. I don't want to get into the details of this, but down the road, I don't think that optimization will be an important use case, simply because you always need to convert your original optimization problem, that is typically what is known as a integer problem, into a quadratic form, that Hamiltonian, that the machine understands, and that overhead can be extremely large. In other words, when you try to scale up to with 1 million variables or so, say something that Amazon Logistics would have, then it's going to be impossible because you need roughly the square of that, so 10 to the 12 variables. But in any case today, it allows us to experiment and see what quantum can and cannot do. And so from my perspective, in the near term, the most important use cases will be optimization to kind of understand where quantum fluctuations help, but also simulation of systems, for example, through machines like D-Wave, where it's a bit more cumbersome, or the QA machine that allows you to create these artificial materials that you can then study experimentally. So when we talk to a customer and they want us to solve a problem, what is the typical work? How do we do this? Let me give you a simple example. That's portfolio optimization in finance. You have a simple problem that to write down. Basically, you want to buy some stock. You want to make sure that if the stock market crashes, or for example, yesterday was September 11th, so the airline industry crashes and you only invest in airline stocks, then you don't want your portfolio to evaporate. And the simple way of doing this is by diversifying. In other words, you buy from different industry segments to make sure that you're not affected by some freak events. And so the problem is very simple. You know, if you have a set of available stocks, which ones do you choose so that they're maximally uncorrelated? But, and here comes the important thing, the gains that you get returns are maximal. And when you sit down and think about it mathematically, you will see that you basically get Hamiltonian on the top right. It's like an AND model. The variables are binary, or they can also be spin 1/2. It's just a constant term that gets added, and some linear terms. And then you can have some constraints, because, for example, certain stocks, you know, you want to have fixed numbers, or you don't want the returns to go under a specific number, et cetera, et cetera. And these constraints need to be somehow folded into this Hamiltonian, and this is where a lot of this overhead happens. But anyways, so now you have your mathematical formulation, and now you have to choose how to solve the problem. And you have many different ways. You can use, for example, the D-Wave quantum annealer and run quantum annealing on it. You can use IonQ's machine and do this via QAOA. You can use classical QUBO solvers like AlphaQUBO by meta-analytics, or you can actually use commercial products like Gurobi that allow you to solve these problems. And this is what people typically do in industry. And then you, of course, get your result. But you see, the important step here is actually the mathematical encoding, because depending on how you do, it will be more effective to be run on a quantum device versus a classical device. And this is where a lot of the thought has to come into. And this is what we do in our team. Now, oops, I see there's a typo there, apologies. How do we engage? So we have three main pillars. On one hand, we like to collaborate with our customers. There's a simple reason for that. We're, for example, not expert in robot motion planning or finance, so we need help from experts. This allows us to enable them, to upskill them and teach them some of the quantum methods we do. And then, of course, we want to solve the problems. And something that is very dear to me is solving the problems in a way that tell us, okay, will this be a good use case for a quantum device? But ideally also that gives our customers the opportunity to actually improve their operations today. And for that, you have to be creative. So usually you start with a problem, for example, optimization. Then we think about how we would solve it in a quantum device. But then we want to also know if this quantum device down the road be the best approach. So we need to raise the bar classically. For that, we basically use adjacent technologies like machine learning and high performance computing or hybrid solutions to then solve these problems at scale. And so our mission is very simple. We want to prepare the customers for quantum sure, but also build solutions that bring value today. And I'll show you 3 or 4 examples in a little bit. So let's go back to portfolio optimization, just to show you how you would solve it on a quantum machine and how you also solve it on a different classical or physics/classical approach. So let's take a simple problem of 8 stocks that have correlations. Typically in financial, you're talking between 1,000 and 10,000 stocks. So this is a tiny example. And the correlations are, in this case, between Walmart, Netflix, BMW, and 3M, or for example, Amazon, Microsoft, Walmart, and Netflix. You can see that certain industries can correlate for different reasons. So for example, if it's the industry, then there are correlations, etc. And then you have to choose buy or not buy, or 0 or 1, which gives you 2 to the 8 combinations. Notice that if you have 1,000 stocks, you have a 2 to the 1,000 combination, so it gets pretty hard. And so it's a very simple way of solving the problem. You basically want to search for what is known as the maximum independent set. I will explain this in the next slide. So that you find the largest set of uncorrelated assets to reduce risk. You can then write this down as a Hamiltonian, and then you can solve this either via a D-Wave device or hardware made by QA. Now, how can you solve this? The idea that we had is, in addition to doing experiments on quantum devices, first you represent the problem as a Hamiltonian, and then you leverage classical technologies to solve the problem at scale. So in this case, we used graph neural networks. And graph neural or neural networks in general have the advantage that are massively parallel because you update all variables at each step, meaning that you can take advantage of cloud computing and really solve very, very large problems at scale. But the advantage of this is that now we also have a mathematical representation that will work on a quantum machine. Excuse me. So let me come back to the maximum independent set. What is it actually? Basically, I can show an example here on the right-hand side. The dots here, for example, are different stockers like BMW, 3M, and so. And the lines mean that a line connecting 2 dots means that these 2 are correlated. And now the goal is very simple: find a set of variables that is not in a set with other variables. In other words, find a set where no variable is connected to another one of the same color. So an example would be these 2 blue dots here. You see that if you follow the lines, no blue dot will connect to no other blue dot. And then what you have to find is the maximum or the largest number of these uncorrelated blue dots. And that is your maximum independent set. It's a very hard problem to solve. And I will show you in a bit benchmarks on 5 regular graphs. And I'll compare to the best known heuristic, which is the Bopana-Haldorson algorithm. So what does it look like mathematically? Here's again, the 8 stocks that I mentioned before, and this is what the graph of correlation looks like. You said X equals 1 if the ticker is in the set, 0 otherwise. And you can then write this down. You see, you want to maximize the number of uncorrelated sets. In other words, you want to have these X's here to be all 0. And then you have a penalty term that makes sure that the constraints, the correlations are kept. And then a matrix Aij that says, for example, if Walmart is connected to 3M, then basically it's 1, otherwise it's or P, otherwise it's 0. And then you can minimize it with D-Wave or any other type of machine. And so in our little 8 stock example, you can see that if you buy, and I cannot see the top right port, but if you buy Amazon, Coca-Cola, and 3M, you're relatively safe. Now, mathematically, if you have a graph like the one I show you on the right, as I said, you can encode matrix Aij in the form that I showed you, where every time a line between 2 of the circles, put a 1, otherwise 0. You can then basically put it down as a cubo for quadratic unconstrained binary optimization problem. In the case of the maximum dependent set Hamiltonian, you have this diagonal -1s, and then you the penalties multiplied by any constant. And then you can either say, I'll solve it on a quantum machine, or you can relax the problem and create a loss function where the binary values turn into these probabilities. You can then train a new network system. And then once you have that, you get probabilities that are between 0 and you can see that, for example, here, variable 0 or variable 1s and 2 that are red probably are any number between 1/2. And so you project them out the values, and then you obtain a approximation to the independent set. And this works extremely well. We use these 5 regular graphs just because there's some analytical results that allow us to compare. But I think more interesting is to just show you the runtime of this approach. The orange dots here are the best classical heuristic, and you can see that it scales roughly as n-cubed. Whereas the machine learning approach that uses this Hamiltonian representation actually scales pretty much linearly asymptotically, which means that we can easily solve a problem of 1 million variables in about 10 minutes. And you see that now we've really raised the bar for quantum machines because we can develop these methods inspired by the way we would have solved this on a quantum device. But we also know now that this problem probably is going to be a long time before it's of value to financial customers if they want to run it on a quantum analog machine. So in the last bit of this presentation, I want to show you a few quantum use cases that we've looked at. And I'm going to start with one that is actually really cool and neat. Oh, no, I'm not. I'm going to first give you an overview of some of the things that we have seen. Apologies. I got excited about what's coming in the next slide. We've looked at very different industry segments, and I just show you here a handful of examples. So for example, healthcare, finance, automotive. And then when we talk to customers in the real world, they often ask us about pretty same problems. Can you protein design on a computer? Can you do molecular similarity? Can you do risk analysis? Can you look at fluid dynamics, et cetera, et cetera? And so we get down and think about how you can see these problems, and then basically figure out, okay, maybe we should approach it with this tool or this tool. And so the colorful boxes that I put here represent, very broadly speaking, the approaches used. So an OR box means that you can easily solve machine learning. So for example, protein design, I think AlphaFold has raised bar to a point where it's going to be very hard for other approaches to compete. You can use a quantitative solution that runs on a fault-tolerant machine, where in principle, there should be an advantage. I say in principle. These are the ones that are the blue squares. You see, for example, that quantum simulation is something that you would obviously do. You could do scheduling. It's going to be painful, but in principle possible. And then finally, you have the red cubes, where I wrote QIO/HPC. What does this mean? HPC means a standard high performance computing solution, where you come in and run this on a supercomputer with some classical algorithms, for example, for fluid dynamics. And QIO stands for quantum inspired optimization, which is a term that is commonly used that I find misleading, which is why I like to call it NIO, for nature inspired optimization, where you leverage physics-based algorithms for industrial problems. Now you might say, well, don't people do this? And I can show you a beautiful example. Right here, I have a book, which is the Handbook of Applied Optimization. I think you can see it's extremely thick. And in this whole book, there are exactly 2 pages devoted to simulated annealing and nothing else about physics algorithms. And so there's many, many low-hanging fruit. And this is why we've been so successful in looking at some of these problems through the eye of a physicist and seeing them bringing value to customers. But you can see very nicely that there's a broad spectrum of ways of solving these problems, things like circuit synthesis, risk analysis, et cetera, et cetera. We can also go a little bit further, look at energy. Again, there's many ways of solving this. But long story short, as you can see, there's a lot to be done. And in particular, you can see there's many blue dots missing. In other words, we still have to think quite a bit on how we would solve this problem on a fault-tolerant machine for a particular industry case. So I don't think I'll run out of business anytime soon, at least I hope so. So now let me show you some of the use cases that we've looked at. The first one here is a so-called binary paint shop problem. This is work that was done by the Volkswagen Group with help from my team. And the problem is very simple. You see it here on the top left. You have a line of car orders that are coming in, excuse me. And the orders come in randomly. And so what you do is when you paint the car, say in this case, blue and pink, you want to make sure that you switch the paint as little as possible because it's a tedious process that wastes also material. And you see that in the center line, you do 3 paint switches is a not optimal solution. And so what you then want to do is you want to reorder the orders such that in this case, for example, you only switch the paint twice. How do we solve this? We looked at this for a very small set of vehicles, did a proof of concept using QAOA on IonQ's hardware, and demonstrated that in principle, it's feasible to solve this problem effectively on a quantum device. But then we said, well, let's go back to this and look at this at scale for a real production line. And again, once we had the mathematical representation to look at this, for example, in this case via IonQ or D-Wave, we were able to go back and say, well, with graph neural networks, we can solve this in a way that would be valuable to companies like, say, Volkswagen, for example. And the beauty is, again, that you can apply this to many other problems. The next one is far more complicated, and I'd like to start by showing you a video. What you see here is 4 robots in BMW's production line, and they're applying PVC seams to the cars. And so the problem is very easily described. You have these 4 robots. You want to make sure the seams are all applied, least amount of material needed, and in the shortest amount of time, with the constraint, you do not want those robots to actually bump into each other or bump into the car. And you can see here, they get very, very close actually to the car body. So it's a very complicated problem. If you want to learn about the mathematical intricacies of this, I encourage you to look at the paper that I list up there. It's highly non-trivial, but basically the goal is to optimize a path with very strong grains in a very constrained volume. And as you might imagine, there's thousands of robots in many companies around the world manufacturing things. So this is a really important problem. How do we solve it? First, did a cubic representation, which I'm not going to read with. It's about 5 lines of equations, and solved it on D-Wave device with a hybrid approach, say in this case, QBSolve. And we're able to show for a small number of seams that it's feasible and that quantum annealers actually work relatively well for this if run in a hybrid mode. And then we said, well, how else can we solve this? So we did one of these nature-inspired algorithms. Dual annealing DA is an approach that basically simulated annealing on stairs. and RKO stands for a random optimizer. That is a traditional tool from optimization. And we married those two, and then we're able to get a 10% improvement in the robot runtime. Now, this might not sound like a lot, but it actually is quite a lot if you think about, say, thousands of products that get made on a production line day. And so this, for example, went straight into production at BMW plants. And so let me show you now what this looks like. Oops, what happened here? Oh, okay. So first you add vertices, then you connect them. And now this is the space where you have to find a solution. And when you do, you get them in robot motion. You'll see these boxes represent the excluded volumes to make sure they don't bump on each other. And this green line is actually what basically the software sees in the simulator. And you can see that, for example, the third robot took a little longer to get to all it seems. But you also see that, the abstract problem to study on a quantum computer can actually carry over to a real industry problem, which is what we're right here. Now, second to last use case, and I'll be done. Options pricing. That's a very important problem in financial institutions. Those are financial products. One of the most CPU-intensive applications in the cloud today. Problem is that you have these stochastic differential equations that represent blocks. They have correlated norms. And it's very hard to solve. You could do it transform, but if you have, for example, 10 equations, you need 100K values, then you can math over how many K values you have to add, and so Fourier transform is not going to be effective. So what people do is run this on Monte Carlo. Problem is Monte Carlo convert relatively slowly, and this is you use millions and millions of cores to actually study these problems for different financial institutions. We sat down, in this case, with Goldman Sachs to look at, we solved this problem on a fault-tolerant machine, and we did an end-to-end risk estimation from data ingestion to operation to output. And of course, found it's going to be very, very painful. And we turned around and said, well, can a method that is very popular in computational physics, known as tensor networks, that are used to basically study quantum system scale, and can repurpose this for options? The answer is you can, because you can approximate quantum Fourier transform with these tensor networks. And now you can get this Fourier transform in approximate manner, but the approximation is enough, except that it, in some cases, a million beta over standard Morton technique. And so you see we now leverage, again, an algorithm from quantum physics in a real-world application, and we can solve now these problems at scale. In this case, customer that I cannot disclose yet. Final one is fraud detection. And I'm just going to keep it full. There's ways of fraud detection. Data are typically based. So what you can do is you can analyze graph structure and apply a scoring mechanism. From that, you can detect transactions. And I don't need to tell you that what is ramping around. So no surprise that it's very important use. And what you can do is you can write down easy Hamiltonian. We can write down up Hamiltonian, and then convert it to an easy Hamiltonian with ancillary variable, and then solve it case like with it on a D-Wave device to demonstrate that approach works. It gives you the number of communities in the graphs. For example, in the bottom left here, you see that they're all kind of grouped, but you have these 5 green ones that are a bit outliers. So potentially those fraudulent transactions. And then you use this score mechanism. You just use Amazon detector, which is that runs in the cloud, to then see is it fraud or not. We can also scale it up with graph networks. The advantage is we don't have to convert it to an Ising model. We can leave it as Potts variables, and we can again have millions of transactions today on a classical computer. And so I'd like to finish. I think it's time to really think about quantum applications, because we don't know yet what quantum computing will deliver value. Also, more importantly, because we need to find better ways and better algorithms to study these problems, also classically, but all quantum with quantum devices. And then
Helmut,
do this is
your sound has been broken. It's like I don't know. It's in the past 5 minutes there has been a bit like fragmented. I don't know if there's a microphone issue. Okay, you could try now. Okay, go ahead.
Can you hear me now?
Now it's much better.
Okay, apologies. Not sure what happened there. So as I was saying, I think it's now time to explore quantum applications. Why? Because we don't know yet where quantum computing will deliver value. And more importantly, because I remember this from my time as an academic, we very often look at these problems with benchmarks that are very simple. You know, think about Ising models, just random Ising models. And the real world is much, much more complicated than that. We like to do this by co-creation with our customers, but also by organizing innovation challenges like the one we did with BMW in the past. And I think that's very important because it allows us to get the brightest minds in industry, academia, startups, etc., to look at these problems. And more importantly, we want to build also this use case portfolio for quantum devices. But one thing that is very dear to me is we need to stop the hype that we have in the quantum community with claims that are inflated and distill out the right use cases so that we can make sure that we can solve these complicated problems in the future. And with this, thank you for your attention.
Okay, thank you very much for a very nice talk. And I agree what you're saying. There's a lot of hype in the field, but hopefully in the next decade or so, important applications will appear in many fields. So let me click here on the chat here. On the chat. Okay, the only comments on the chat was about the sound voice breaking out. But right now, after you made a change on the microphone, whatever, the sound became much better.
Yeah, apologies for that.
And then, right now I see on your screen there is like the symbol of the speaker.
Yeah, I have no idea what's going on there.
Okay, it's okay. So
yeah, no idea.
So therefore, if you look at your slide number 26, quick question. So there is the pane switch problem.
Yes.
Could this be seen as a trivial problem where you're trying to do first all the cars of color A, then you stop, then all the cars color B, then C. So that would be the way to find the absolute minimum number of pane switches, no? Wouldn't be just, there is no NP completeness. It seems to be like fairly simple.
Well, it's not that simple because there is a continuous line of orders that never ends. And sometimes production will catch up, then there will be delays and so on. So it's not that you can, you cannot predict what's coming at you. That's the problem.
Oh, I see, because I assume there is a list of colors. At that point, you can just we do all the greens or the blues or the reds or the purples, and then, but if they keep coming, then that's a problem because then.
Exactly. That's the problem. You see, otherwise, I agree with you. You just move all the red ones to one side, all the blue ones to the other, and you're done. But you don't know what's coming next. And while it's coming in, you're already working on a car, so you might have switched to paint, if you see what I mean. And so it gets really complicated quickly.
In the case of quantum chemistry or quantum materials, people try to use quantum computing for small molecules, then they're doable, very tiny ones. But then as soon as you go to not so small molecules, it can get complicated very, very fast.
Yes.
So for people say, okay, the Hilbert space has, let's say, gazillion qubits, but if you look at the symmetries, you're looking at gazillion. We need to just look at a few billion. And if you look at the more symmetries, you might be lucky to get only a few million qubits. But still, after massive amount of symmetries from what we're seeing in our group, and we used to work on this like many years ago, then we stopped like, and then it did seem to be like a lot of qubits needed. So therefore, that's to be doing even simple molecules. So therefore, the hope, the wish, and the dream is that eventually people might find more tricks, perhaps not only quantum computing plus machine learning together, working together, moving many knobs to be able to do the push, not just gazillion to billion to million, but perhaps 2 million to 1,000, few thousand qubits, hopefully a few hundreds, which
Exactly.
maybe.
Exactly. And I fully agree with what you said. You know, this is why I emphasize hybrid solutions, because the quantum machine alone is not going to have the ability to do this. And the classical machines have also limitations. So we need to start mixing the technologies. And this is exactly what we're looking at today.
No, this is exciting. This
for some reason, I can't hear you now.
now, can you hear me now? Hello, can you hear me, Helmut?
Well, my computer, 1 second.
I can hear you. I can hear you, so perhaps might be like a microphone issues on. You're connecting in a different channel. I see.
So apologies for that, but my computer died. And so, yes, thank you about that.
Okay, our condolences for the loss of the computer. So let me see, let me click on the question and answer, see there are more. Oh, here it is. So somebody's saying the volume is off. Okay, but it's taken care of.
Right. Please, I have a question, a quick question. So when you, for the stocks, when you write the Hamiltonian, isn't a mean field approximation enough? A mean field solution enough? No?
No,
Okay.
it's actually, it's not enough, unfortunately.
Okay. Okay. Thank you.
I see the. So, any more questions on the audience there in Kigali, or some other ones?
Online, somebody is asking about the quantum random generator. Can they give business value?
So
can they give business value, quantum number generators?
That's an interesting question. You know, if you need truly random numbers, then the answer is yes. And there's machines that can do this today, but their clock speeds are not fast enough yet. And you need probably like provable random numbers, for example, to seed virtual machines in the cloud. So it's an important use case. And so they can deliver value, but we yet have to find the quantum version of doing this that actually does it fast enough for applications, say like Monte Carlo, for example.
Yeah, the typical ones might be integration for Monte Carlo, or like, and also it might be some applications in gambling, no? Because if you need to have a random number generator for some gambling, or for yeah, I think it's Monte Carlo might be like for integration the most useful.
Yeah, absolutely.
And then there was another question. How do you feel about running cybersecurity on the multi-quantum computer? I don't know what the question means. How do you feel about running cybersecurity on the multi-quantum computer?
I think I understand it, and if I'm wrong, I apologize. Basically, I think the question is, if you have multiple quantum devices, how can you make sure that they're safe to cyber attacks? And the answer is, it's actually relatively simple, because the quantum devices are always connected to a classical device so that they can actually talk to the rest of the cloud. And so as long as the cloud is secure, the quantum machine is secure because it's in a sandbox environment.
Okay. So thank you very much. Let's thank Helmut again.
Oh, but before Helmut leaves right now, well, let's thank for the great talk.
Thank you.
Before Helmut leaves, this is a coincidence. Helmut is originally from Peru. Fernando is from Brazil. I'm from Venezuela. So this is like three neighbors who just happened to be meeting in the global south, but in a different part of the global south. It is like the director is also part of the global south, but different part of it. So it's a coincidence here. And then, it was great having Helmut. It was very interesting talk on many different topics, and I had many questions I thought here, but I think I'll better ask to you later on some other day because there are like too many questions.
Sounds good.